Maybe not.
You can use it. Which one is for Zoom? This one?
I don't know which is which. Is this, let's see. Is this the room microphone, I think? So probably the other one is the room. All right. Good morning, everyone. Hopefully the people in Zoom can hear us okay. Please let us know. We have a pretty decent number of participants. Okay, very good. So I think we'll go ahead and get started here. So today it's our pleasure to have our own Kejie Fang from Electrical and Computer Engineering speaking us today. So Kejie received his bachelor's from Peking University and then went on to do a PhD in physics at Stanford, where he graduated in 2013, working with Shanhu Fan. He then went to Caltech to do a postdoc with Oscar Painter, where he was there until starting a faculty position here in 2018. He works on quantum photonics, as he'll tell us about. He's won a few awards already, NSF Career Award and the DARPA Young Faculty Award. So it's our pleasure to have Kejie, and Kejie, please go ahead.
Thank you, Jake, for the introduction, and thanks for the invitation. So I guess COVID brings a lot of inconvenience, but the one convenience is you can give talks online. And also now it's also convenient to give a talk 2 blocks away in a building. So, so today I'm going to talk about our recent work towards realizing single-photon nonlinearity in photonic integrated circuits. And it combines some theory and experiment work, and I will talk about our theory and then our photonic integrated platform, and also our ongoing experiment. So before we talk about single photon nonlinearity, I will briefly mention where this all started, right? So our platform is based on nonlinear optics. Essentially is, you know, the permittivity of any material is almost nonlinear, depending on the intensity or the electric field to some level. Although the nonlinearity is usually very, very weak. So about 60 years ago, this is the first demonstration of generation of higher harmonics in nonlinear crystals. So essentially, because permittivity depends on the electric field, if you send in a light, it will generate higher harmonics. So this is the first demonstration. Because the effect is so weak, there is a famous story that the editor actually removed the signal. Okay, they send in a fundamental light and generate a second harmonic at double the frequency. But somehow the signal is so weak, the editor removed this point, which was thought to be a dust. But since then, nonlinear optics turns out to be a very powerful technique in science and technology. It has many applications from spectroscopy to sensing. And of course, it finds its application in quantum information processing. However, because of weak bulk optical nonlinearity based on Chi2 and Chi3 permittivity, usually people when using optical nonlinearity for quantum information processing, usually it's a combination of nonlinear sources and linear optics. What I mean is that we need quantum light sources for optical information processing, and these nonlinear sources, they could be single photons, and they could be generated by using bulk nonlinear crystals via Chi2 and Chi3 processes. Okay, so here is a few examples based on, for example, periodic pole, lithium niobate waveguide, and microring resonators and long coiled waveguides. And then with these non-classical light sources, you can pass these single photons through a linear optical circuit. Okay, linear optical circuit consisting of couplers and waveguide. But we know that in order to do universal quantum information processing, you do need to have nonlinear quantum logic, such as conditional NOT gate or conditional phase gate between two single photons. But the nonlinearity, bulk nonlinearity is so weak, you won't be able to realize these kind of nonlinear quantum gates between two photons. What you do instead is to use a measurement induced nonlinearity, okay? By measuring part of the photons and conditioned upon the measurement outcome, that will herald a effective C-NOT gate or C-phase gate on the remaining photons. Okay, so this is a measurement-based scheme. The architecture is a linear optical components combined with measurement and feed forward in order to do universal quantum information processing. And certainly you realize this is a problem with that is it is probabilistic in nature, and it becomes difficult to scale up if we want to do more complicated information processing involving many measurements. And there are other special type of information processing, such as boson sampling, where again you use the linear optical components, waveguide couplers, but not aiming at universal quantum computing, but for certain specific information processing. So you can also do that using linear components combined with nonlinear sources. And also you can, the nonlinear sources could also be continuous variable sources such as squeezed light. And there are also universal quantum computing schemes using the kind of continuous variable quantum lights. Okay. However, it turns out it will be actually very useful if we can indeed have nonlinear effect at a single photon level, right? Because that's essentially the foundation of cavity, other quantum systems such as cavity QED, where people can realize the nonlinear effect between single photons. So people are indeed trying to, realize single photon level bulk nonlinear processes. So these are some works almost a decade ago. So on the left is from a group from University of Waterloo. And what they did essentially is they studied this kind of nonlinear process at a single photon level. Okay, they're sending a pump laser and they go through this spontaneous parametric down conversion process. And the down conversion process only generates a pair of single photons instead of many. And one of the photon actually will serve as a pump for a secondary spontaneous parametric down conversion and generate another pair of single photons. Okay, so this is still similar to the conventional spontaneous parametric down conversion. However, they operate at a single photon level. So you can imagine now, and they want to measure the correlations between the down converted 3 photons, 1, 2, 3. Okay, so now you can imagine the event generation rate will be very low because they use these bulk crystals. Okay, they can collect tens of events, 3 photon events in about a day. Nevertheless, they are able to measure some non-classical correlations between these 3 photons. Yeah, I think, yeah, you can. Yeah. Right. This is consistent. Yeah. Oh, I see. Yeah, Jim is asking if this experimental result is consistent with theory. So essentially, yeah, this rate can be predicted by theory, considering the bulk nonlinearity. On the right is another similar nonlinear process, but they use the second harmonic, some free frequency generation instead of down conversion. So they have 2 SPDC sources, and they actually use 1 photon from each source and combine them through a some frequency generation process and give you a single photon that is frequency that is sum of the 2. And there's some experimental demonstration and measure the correlation between these 3 photons. Okay, so So it turns out that despite these effects, bulk nonlinear optical effect is very, very weak at the single photon level. There is some theory work saying that, okay, if we can achieve certain nonlinear efficiency, such that, for example, here, if we can have some frequency generation efficiency on the order of 10 to the minus 9, still this can beat linear optical schemes, okay, for heralding maximally entangled states. So this is actually very interesting. Certainly, this is 10 years ago. There is the more advanced linear optical schemes that has a much higher efficiency for generating heralded maximally entangled state. But also keep in mind the nonlinear efficiency we can achieve now is also orders of magnitude higher. So in a work I will show, our work shows that this coefficient, this efficiency is now on the order of 10 to the minus 4. So 5 orders higher than this theory work is done. Okay, so this coefficient actually turns out to be a very important figure of merit to characterize the single photon nonlinearity. Okay, essentially this is G over kappa. G is the nonlinear mode coupling. If you have a nonlinear crystal, you have 3 modes together. You can calculate the single photon interaction between these 3 modes. So that is the G, nonlinear interaction strength, over kappa. Kappa is the loss rate of photon inside of the crystal or in the system. So this essentially measures the strength of single photon nonlinearity, just like a cavity QED systems. Okay, so these experiments, they essentially still they are still like a parametric process, but operate at a single photon level. What we are interested in is actually this question: whether we can realize photon-photon interactions via bulk nonlinearity. So here the setting essentially, I have 2 random single photons coming in. They are not pumped. They are not parametric pumps. There are 2 separate random photons coming in through a nonlinear optical system. Okay, this nonlinear system, because it is based on bulk optical nonlinearity, the nonlinearity is very weak, characterized by G over kappa, this ratio much less than 1. Okay, so we asked is it possible to have the output photons have non-classical correlations, right? Intuitively, you would imagine, you will not have observable non-classical correlation between these 2 photons because most of the time they will not interact with each other. Okay, but nevertheless, if we can come up with a scheme to have photon-photon interaction via weak bulk optical nonlinearity, we can realize all sorts of useful and interesting quantum optical effects and find applications of quantum information processing. For example, we can write photon blockade. Okay, we can have a few photon correlations and have non-classical correlations between a few photons that propagate through this nonlinear system, nonlinear optical system. And in terms of application, if we have a 2-photon interaction, we could have use that to realize a quantum non-demolition measurement. Okay, using 1 photon as idler, another one as a signal. We can realize quantum logic. We can also, these QND measurement is critical for quantum repeaters. Okay, so that's our question, and we carried out some theory and experimental work, and that's what I'm going to talk about. So I will first talk about a quantum optical scheme we thought about, and then I will show our we developed a new integral photonic platform, gives you a record high G over kappa ratio. Okay, and then we'll show some our ongoing measurement experiment of photon correlation measurement via this kind of system. Okay, so our protocol is based on a waveguide coupled nonlinear optical cavity. So here what I show is a typical optical cavity, which is a micro-ring resonator, which supports 2 modes. One is at the frequency omega, another at the frequency 2 omega. Okay, you can make the kind of ring pretty easily. And this ring is made from Chi2 materials. We choose Chi2 is because Chi2 is a stronger nonlinearity than Chi3. And this micro ring is coupled to a waveguide. Okay, and we can send in photons from left and measure photons, output photons from right. So this is the So this is essentially an open quantum system, right? Because we have input output, and the photons in the ring could also decay into the environment. Yeah, in our experiment, is the frequency is 200 terahertz with telecom wavelength band. 200 terahertz, yeah, for the fundamental mode. So this is essentially an open quantum system, and we can use effective Hamiltonian to describe it, right? This term is it's a free energy part, okay? And for mode A and mode B, we also included a loss rate of the two modes, right? Including both the external loss rate into the waveguide and the intrinsic loss rate that could due to the material absorption. Similarly for mode B, and then finally we have a Chi2 induced nonlinear mode interaction. Essentially, is one B mode photon can convert to two A mode photons. Okay, so and then we have input-output relation. Right, input we have input. It could directly transmit through waveguide, or it can couple into the cavity, then cavity decay into the waveguide again. So this is typical input-output formalism used in quantum optics. So here we have a requirement. We would require frequency and phase matching between the two modes in order to have a large nonlinear interaction. And of course, we are constraining ourselves in the reality where this coupling is very, very weak, much smaller than the decay rate of these modes. Yeah, I'm gonna show, so you can use any nonlinear material. So right now I'm just talking about our scheme, our theory. Next, I will talk about our material platform, yeah. Yeah, the theory doesn't matter, right? The experiment is, yes, we did it for 1.5 micron. Yeah, you can think store, but it's not storing. It's just the ring itself supports this kind of mode. When you send the light in, the light will be circulating the ring with within the resonance. Many times. Yeah, many times. Right. Yeah. So it's actually in this, we've got a QED architecture. There are tons of theory and experiment work in this field, and here I just listed a few literatures. And this highlighted red one is the one I think appeared recent years from my PhD advisor group, and they actually come up with a theory formalism allows you to calculate a few photon transport through a nonlinear system, okay, based on quantum field theory. Because if you think about this problem, it's essentially very similar to the particle scattering in quantum field theory. So they can use this S matrix formalism to do the calculation rigorously. What we did in this paper is essentially we consider weak nonlinear systems. So essentially that quantum field theory based approach, you can actually come up with Feynman diagram approach in order to do a very straightforward and intuitive calculation of the weak nonlinear system. And that's essentially what we did. We come up with a Feynman diagram approach and apply it to this system. And then we find a intrinsic particle we can use to realize photon-photon interaction. So let's look at this system again. Here, I'm going to show how we can use this system to tailor the two-photon wave function. Okay, so we start with a single photon, right? A single photon through this system. Then this is here. There's no quantum optics. It's just people know in nanophotonics, if you send the photon in, it will either direct transmission through the waveguide or couple into the cavity and then come out. The two paths will interfere, and you can calculate the linear transmission coefficient. Okay, and because of the interference through direct and ring coupled paths, you have this. You can find that this linear transmission could be annihilated when near the critical coupling regime, meaning the kappa I equals kappa E. Kappa I basically the intrinsic loss rate equals the external loss rate. So it's sort of like an impedance matching process. Okay, so for single photon coming in, because the impedance match, it will decay into the internal loss channel without transmission. So this is single photon transmission. So now if you consider two photon transmission, right? Now the two photon transmission, there are two different choices for the two photon. They could, both of them could transmit, right? Just as if, so they don't interact with each other, they just transmit. So then the transmission is simply T squared because you have two photons. And another path is via the interaction in the ring. And so you have two photons. They are at fundamental frequency, which is 200 terahertz in our case. And they could interact and then convert to a second harmonic photon. And then this second harmonic photon could decay into the two fundamental photons again. All right. So this process is actually virtual. It doesn't necessarily mean a real second harmonic photon is generated in this process. It's essentially a virtual process or due to quantum fluctuation. But nevertheless, this scattering amplitude will be there because of this nonlinear interaction in this micro ring. Oh, this amplitude corresponding to this virtual process, you can do a yeah, Paul.
Less likely than just doing the conversion.
Yeah, so the question is that how about the real second harmonic generation process, right? So that will happen, right? That will happen. That means there is a certain probability that is two photons coming will convert to a real second harmonic photon. They will be lost. But what we care about, yeah, there will be loss. But what we care about is this two photon wave function, and essentially is that for this process to happen, there is still a probability which is measured by, I will show you, it's actually measured by T squared because that is essentially the photon flux out of the system. So there will be a small photon flux, but for this part of photon flux, they have two photon wave function given by this form, and they have non-Caltech correlations. And here, because of the Chi2 process, the nice thing about it is that the second harmonic frequency is so different from the fundamental one. You can simply, filter it out without influencing the result. So I want to point out that you can actually estimate the scattering amplitude corresponding to this virtual process. Is that each vertex here is an interaction point. Yeah.
In your first process. Or many times that.
Well, so yeah, so the whole process is coherent. You could have this photon could directly go through the waveguide, or it could go around this ring many times. But these processes, it's a single photon pulse. Then the dynamics, you need to consider the detailed dynamics, right? What I mentioned here is a CW case, a continuous wave case, gives you this transmission coefficient. Yeah. Yeah. What am I? So I'm just saying, okay, this amplitude could be easily estimated. Each vertex is an interaction point. So that is proportional to the nonlinear interaction G. And we know the amplitude is a unit list parameter. So it has to be divided by a certain energy scale. And here for the resonance case, the energy scale would be given by the loss rate of the photon, so kappa. So that's why this amplitude magnitude order is given by G over kappa squared. And you notice there are minus sign here. This minus sign is very important for the effect I'm going to talk about. This minus sign, you could think about it as a Rabi flip between the two photons and this blue photon, right? So the nice thing about Chi2 is that this two photon and this single photon form a closed subspace. So two fundamental photons coming will convert to a single second harmonic photon, and then this single harmonic photon will then convert to this two fundamental photons again, and this is essentially a Rabi flip. And Rabi flip will give you pi Berry phase. So that's why you have minus sign here. Okay, so now you can realize this two photon wave function is actually a sum of this direct transmission and this interaction mediated transmission. And because of a sign, you can actually cancel these two components. Okay, essentially you can have single photon amplitude out, but you won't have two photon come out. You have single photon wave function, but no a two photon wave function. Two photon amplitude is 0. And this is essentially the photon blockade, right? This is essentially photon blockade. You can have photon stream, but if you measure two photons, you won't get two photon events simultaneously. So you can do a rigorous calculation. The normalized second correlation function is given by the two photon wave function divided by the square of the single photon wave function, and the two photon wave function as shown is just the superposition of the two paths, right? T squared plus the capital T. And indeed, because of the sign of the T, right? By choosing the proper parameters of the device, including the loss rate and the coupling rate, nonlinear coupling rate, you actually can have a 0 G2, right? 0 G2 0. And this red line corresponding to that case. So this is the pronounced photon blockade effect. And so here is what I do is we choose different intrinsic and external loss rate. And when they close to the matching condition, you have when T squared is T squared is close to T, then you can have this cancellation. And for the plot, I also choose G over kappa about 1%, which is actually what we achieved in our nonlinear photonic platforms. Okay, so you can measure these two photon correlations. Very simple. You have output photons and send it to a split into two paths and measure the correlations. And I also want to mention that there are also other schemes to realize photon blockade based on weak nonlinearity. One is the unconventional photon blockade. There is you actually also use quantum interference effect, but that quantum interference is via different interaction passes. Okay, interaction passes, and you can also realize photon blockade. And in recent years, and there are a dynamic driving scheme which allows you to realize photon blockade. The photon blockade is just one effect. We can also, this kind of photon penetration also gives you nonlinear phase shift. So here imagine is that you have a single photon coming into the system that gives you 0 phase shift. But now if you send a two photon coming in, it will give you a nonlinear phase shift. And this is essential, you know, for QND measurement. If the two photons have different frequencies. So here again, I show the same set of parameters. And I plot the calculated nonlinear phase shift, and you see that in certain range, in certain frequency range, this nonlinear phase shift could be large, and it also can approach pi. Yeah, essentially that. That's. Yeah. That's right. So this is a frequency relative to the resonance frequency of the fundamental mode. So here essentially tells you basically need to be operated at very near to the resonance condition. Okay. Resonance condition meaning the frequency of the light coming in is the same as the frequency of the resonance of the ring resonator. The cavity. Yeah. So it needs to be aligned very well with the cavity frequency. Kappa is on the order gigahertz. Yeah. Yeah. Yeah, right. If you want to operate at a pulse range, yes, you need to have long pulses. Long pulses. Match the
basically.
Right.
So now I'm confused.
For this, right, you want long pulses such that it's frequency pure and you can use this resonance condition. If you have long pulses, essentially all these effects will be reduced by a certain factor by averaging. So you reduce the effect. Yeah. So this kind of nonlinear phase shift is basically you can use that for QND measurement, right? You have two photons, and one is a signal, another idler, and you induce a phase shift on the idler, and use that to determine whether there is a single photon that is passes through. And this QND measurement again can be used for quantum repeaters, right? It's a foundational quantum repeater. You can use that to tell when the single photon comes in, and then release a photon from quantum memory to do Bell-string measurement, and then create a distributed entanglement in the quantum network. Okay, I should speed up. So here's essentially a summary of our scheme. Essentially, we want to use the direct transmission and the interaction-mediated transmission via a Chi2 cavity, and if we are able to tune this direct transmission to be close to this interaction-mediated amplitude, then we can realize the interesting quantum Auto effect. So keep in mind that this T is proportional to this ratio, and in reality, it will be pretty small. That means in order to see non-trivial effect, we need to be tuned T squared to be close to this value to be small. And it turns out this is highly non-trivial in integral photonics. But the first thing still is that we want to ramp up the value of T as much as possible so that we don't have to attenuate little t too much. No, T squared is a linear process. It's a linear process.
This is why we end up
here. So our goal is still to try to have G over kappa, this ratio, as large as possible, and we need to have nonlinear materials. Have a large Chi2 parameter. So we choose indium gallium phosphide. So it has a large Chi2 parameter. It also has a relatively large band gap such that it won't be limited by two-photon absorption. There are also other nonlinear material. You've heard of lithium niobate, right? However, it has still have smaller Chi2 parameter than the in gap. There are other 3-5 materials. The material turns out to have some loss mechanism of them, so that's why we did not choose the materials. So our material, the in gap, choose the material. We can grow the materials epitaxically, and this is basically the fabrication flow. The key part is that realizing this in gap is grown on gas, which they are index matched. So eventually we have to undercut the in gap material such that we can confine light in the device layer. Okay, so this is the key of this fabrication process. So this is here on the right. We show the some SEM image of the fabricated circuit. We have micro ring. We have two waveguides. One is for guiding 1550 light. Another is for guiding 775 light. And the in gap, eventually we have 115 nanometer thickness, and we use a membrane of oxide to suspend this ring, to mechanically anchor this ring. So why we have this thickness? Because there is some design details in there. So in order to, because of the in gap has zinc blend crystal structure, it has chi XYZ tensor. So we choose the TE and the TM mode for the 1550 and the 775 wavelengths respectively. And then they have a large field overlap that is consistent with this chi2 tensor to give you large nonlinear coupling. And for a 5 micron range, we have 11 megahertz nonlinear coupling. Okay, and they also need to be designed to be phase matched, right? Phase matched and frequency matched. And turns out, because of dispersion of this material, the phase matching condition is quite stringent. Okay, if we change the in-gap thickness by 1 nanometer, the width of the ring has to be changed by 100 nanometers. But however, because the material we have is pretty smooth. Okay, the thickness variation is very, very small. So in a fabricated device, we can still achieve the phase matching condition. So so this is our, as I showed before, this is our fabricated device. So we did a couple of nonlinear nonlinear optical process. So this is second harmonic generation. So I want to mention that our fabricated ring resonator with radius 5 micron has this pretty high Q. So allows us to have a very large second harmonic generation efficiency. Okay. We also did a reverse process, right? You can do also spontaneous parametric down conversion. Now you send in 775 light and get pairs of 1550 light. So this efficiency, pair generated efficiency is given by about 28 megahertz per microwatts. So we can compare the device performance of our in-gap with other platforms. So here you can see that x-axis essentially compares the noise performance, and y-axis is efficiency. So you can see that we have very high efficiency, and the noise characteristics affect of 2 more because we are using the degenerate process, and this 2 and 6 they use non-degenerate process. So this is still conventional characterization of our device using the parametric nonlinear process. So from there we can infer this key parameter, the G over kappa. So we measure G to be 11 megahertz. Our kappa is about 1 gigahertz, less than 1 gigahertz. So we have a ratio about 1.5%. So we have a plot here to compare our architecture with other architectures, such as lithium niobate, these green dots. Okay, there are also a recent work showing lithium niobate approaching 1%, but we are about 1%. And the key merit of our structure is that we can have very large G instead of very large G, but lithium niobate essentially is by increasing the Q of the cavity to make a G over kappa large. It turns out, increasing Q actually will bring certain nonlinear, certain noise effect. So I think our architecture with the large G is actually more advantage. Okay. Yeah. 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 Right. This is just for doing the 2 parametric process, right? Because I want to measure 775 light, so that's why I also have a 77. Right. The cavity. Yeah. They are all nonlinear materials. It's just this circle is a cavity that could enhance the nonlinearity because the photon will circulate in this cavity. That nonlinear process happens inside the cavity. Okay, so it will happen inside the cavity, and I don't need to purposely separate them. Okay, when they couple out, yeah, 7075 will couple to the other waveguide. Even I don't have this 7075, I'm fine because I can do off-chip wavelength division. That's all fine. Yeah. So, so we have this. We have figure of merit, which is state of the art, and this figure of merit, of course, is related to all the other conventional nonlinear process. So we can achieve this interaction media amplitude about on the order 10 to the -4, and we have a technique to tune the linear transmission of our device to be 10 to the -5 or even lower. Okay, so I want to emphasize this is not like a attenuator, off-chip attenuator. So imagine you have a device, you have off-chip attenuator. If you apply an off-chip attenuator, that will also attenuate this two-photon amplitude, right? So you cannot do off-chip amplitude attenuation. You have to do this on-chip attenuation in situ with this nonlinear interaction in order to observe this nonlinear effect. So we have techniques to do that. So that means, okay, we are almost set. We can actually observe, ideally, we should be able to observe this photon blockade or nonlinear phase shifter. And so first experiment we do is just to measure try to measure the two-photon correlations, okay? So in experiment, we sending a weak coherent state, passing through this device, and we measure the photon correlations. We can operate a device at the cavity photon number about 1, from 0.1 to 10, a few tens, and we can tune the linear transmission of the device to be 10 to the -4, and that means the output photon flux is still on the order of 1 megahertz, and we can operate at a higher frequency, higher rate, because as long as this weaker driving condition is satisfied, this effect will sustain. So we can operate a few tens of megahertz. That's no problem. So that's a rate is actually pretty decent. So we measure the correlation. What we get is this, okay? Instead of a G2 0 less than 1, we actually have this complicated G2 function. All right, you see that there's oscillations, long oscillations. If you zoom in to tau close to 0, I also have fast oscillations. So this puzzles us for quite a long time. So if you can go through a laundry list, right? All these possible causes of G2 0 larger than 1. Okay, so for a long time we worry about our laser, right? Could it be laser threshold? Could it be laser side mode or ASE? At one point, I'm almost convinced it's a laser side mode, and bought a very narrow band filter and put it into our setup, but we got the same G2. So then we keep reading, look at into literature. Okay, if you have feedback in the circuit and feedback into the laser, you could have chaos, and that will cause G2 larger than 1. Some chaotic light, G2 larger than 1. And then I find the papers saying, okay, if there is some vibration of the roughness structure, and the scatter light due to this vibrational roughness will cause G2 larger than 1. Okay, this is experiment of a rotating sandpaper, and they measure G2 of the scatter light, they find G2 larger than 1. And zero dynamic light scattering, people in biology do is that they send light to molecules that is flowing through doing Brownian motion, and that light also gives you G2 larger than 1. So these two actually really inspire me, find the solution of this weird G2 behavior of our device. Okay, it turns out our device is a optomechanical system. Okay, it's actually a optomechanical system. Remember, our device is sitting in a very thin membrane, and the membrane, as you would imagine, at room temperature, due to the thermal occupation of the phonons, they will vibrate. Okay, so that actually is the cause of what we observed of the G2 larger than 0. But this is still a surprise, right? This is very surprising. This is a remarkable, actually remarkable optomechanical system. Remember, I want to point out that previously when people want to use, observe the vibrational mode of membrane, what people use is actually a external fabric pearl optical cavity, right? And then have the optical cavity mode interact with membrane. But here we actually can integrate a optical cavity inside of the membrane, okay, instead of using an external cavity. And that allows us, that actually is a new optomechanical system. So you do some simulation, you find that you can identify a group of vibrational modes. You have membrane modes, right? You can also have a radial breathing mode of the ring itself, and you can calculate the coupling between all the mechanical modes with the optical cavity mode, right? That 1550 nanometer mode, wavelength mode, and they have actually not non-negligible interactions, right? So typically, when you want to observe the mechanical motion, what you do is you have a probe beam that is parked at the slope of a resonance, right? And because of the motion of because of mechanical vibrations, this resonance will jitter, and that will cause the intensity modulation of the transmitted light. And then you send this intensity modulated light into a photodetector, measure noise spectrum, and you can see a bunch of peaks. And they corresponding to the mechanical mode in the device. You have low frequency membrane modes, and you have high frequency ring modes, all right? So what we did is G2, right? So if you do a Fourier transform G2, you find exactly same, almost exact same noise spectrum, okay? So that tells me what we observed, the oscillation in the G2 actually is induced by these vibrational modes in the device. It will be here, but it doesn't matter here, right? Oh yeah, it could be here. Yeah, it could be here.
So it's on top of the membrane.
Yeah, they're all buried, attached to the membrane. They all vibrate. Okay, but yeah, so that's a solution we work for months and finally find out the cause of this weird G2 behavior. And that leads to actually a new optomechanical system. So for this measurement, what we did is that probe light now is in resonance with the cavity mode, right? And the transmission is tuned to be very, very small. So so how this allows us to do this correlation measurement to find out essentially the photon-phonon correlations. So to detect the photon-phonon correlation, right? Optomechanical interaction is essentially a Stokes anti-Stokes scattering. You could have a blue detuned light, right? This here two lines represent the a cavity mode. You can have blue detuned light, and that will convert to a phonon and a resonance light photon. Or you can have a red detuned, then combine with a phonon to convert to a cavity photon. However, so this process is still very, very weak because of the weak optomechanical interaction. So in order to observe this kind of scattering effect, you need to filter out the strong pump or strong probe, right? Typically what you do is you use a external filter, right? Because you use external optical filter, it's more convenient for a large mechanical frequency, such that the probe and the scatter light, they have well-separated frequency. So typically this technique is used to measure gigahertz phonons, all right? But in our system, as I showed before, the frequency of this mode is about megahertz. So it's very hard to use a optical filter with line width about 1 megahertz to do this kind of filtering. So what allows us to measure this photon-phonon correlation is actually, we call it dissipative filtering, okay? Our device itself allows us to filter the probe photon, okay? The red arrow comes in. When the cavity is critically coupled to the waveguide, these probe photons won't transmit through the device, okay? However, the optomechanical interaction induced photons, this yellow arrow, they will couple into the waveguide and transmit it. Okay, there are no cancellation of this yellow arrow, but there is cancellation for the red arrow. So this is due to the dissipation engineering. We engineer the engineered cavity to be critically coupled. So then we can naturally filter out this this probe light. Okay, so this is very interesting because now this is a frequency insensitive. That means even the yellow and the red, they have same frequency. I can still filter out this probe. Okay, it's not frequency selective. It's actually, you know, depending on the origin of the photons, I can filter them out. Yeah.
Sorry, how can we?
Because this photon, as it passes through, the transmission will be 0 if it is critical coupled. This yellow one, because it's not from external, it's generated inside the cavity. So the coupling.
You don't have the other term.
Yeah, exactly. There are no another term. So it's always non-zero, but the red one can be 0. Even they have the same frequency, right? So this has become very useful. So that's why, you know, it essentially allows us to do this photon-phonon correlation measurement for very low frequency mechanical modes. So here is we continue to tune down the linear transmission, right? And the blue is transmission still at 10 to the -3, and you tune it down, you find a more significant effect in the G2. And we can do this for different size of rings, right? You can different size of rings. We all observe this kind of G2, and then corresponding to the measure the mechanical spectrum. So we can do modeling. Essentially, is photon-phonon scattering and a few Feynman diagrams corresponding to the Stokes and Stokes scattering. What I want to use Feynman diagram is because there are actually 2 Feynman diagrams that is non-trivial. These 2 actually correspond to a virtual phonon-mediated interaction between 2 photons, similar to the Chi2 effect. But now the interaction is mediated by the virtual phonons. Of course, we did the experiment for thermomechanics study. We do not observe these quantum process. Okay, but if we really prepare the mechanical mode to mechanical oscillator to be a quantum state, then you will observe effect due to these interactions. So for our thermomechanical oscillator, we can do actually a classical modeling, and we can fit out G2 data pretty well. Okay, so it is a bummer, but it turns out to be a surprise. We are able to measure photon-phonon correlations. This technique can be applied to measure non-classical photon-phonon correlation if we prepare a mechanical oscillator in a quantum state. And this can be applied to optomechanical system with very low mechanical frequency. For example, you know, LIGO, their mechanical frequency is about kilohertz, and you won't be probably very hard to have a optical filter with line width less than 1 kilohertz. And compared to other light scattering process, right? So you can study light scatter from molecule, and these macromolecules, they move very, very slow. So the scatter light will have almost essentially the same frequency as probe light. So in order to measure these scatter light, this kind of dissipative filtering will be useful. So in summary, I showed you that we are working towards a single photon nonlinearity in integral quantum photonic platform. We have the platform, okay? We have a G over kappa about 1%, we have ongoing experiment going on. Along with that, we find that our system right now is actually an optomechanical system. In order to continue this experiment, one simple solution is to make our structure more mechanical, more stable, right? For example, you can increase oxide cladding of our structure, so it's more bulky. So then it's less vibration, or you can do wafer transfer to have a in-gap on oxide structure, and then you completely eliminate the mechanical vibrations. So working on that, and hopefully we could have a few photon quantum correlations from this integrated platform. So this work is done by a few graduate students. So serial worker Yunkai Wang did a lot of calculation, and experimentally Mengdi Zhao carried out the fabrication and took a lot of measurement and data analysis. And recently, there are new students joining this project. Okay, so that's all. Thank you.